Hello, good morning. So you already heard about gravitational waves. So I guess most of the topic here were about astrophysics. So today in this 45 minutes, I want to tell you a little bit of application of gravitational waves to cosmology. After all, cosmology is not a different science than astronomy. It just depends on the distance where your astrophysical sources are. I mean, if it's outside the galaxy, then there must be a cosmological application. Okay, so just to summarize, you remember the output of the gravitational wave detector. So I don't need to give you the basics of gravitational wave detection because Irene already did, but I just want to recap this because it will be crucial to understand the results. So the output is linear. Actually, it doesn't have to be linear, but the gravitational wave amplitude is so small that the linear is more than is more than enough. And so the output of the detector, you remember, there were those two arms, and then the intensity of the recombined light changed with the differential length of the arm is proportional to the two polarization. Of course, gravitational wave arrives in two polarization, no? Like photons, like light. Light has two polarization. Gravitational waves has also two polarizations. Basically, these are the only two massless fields that we encounter in nature. But of course, the output of the polarization doesn't need to be exactly one polarization or exactly the other. It must be a mixture of the two. And the two coefficients, by definition, are called F plus and F cross. And this is quite universal. In all paper and books, you find them called F plus and F cross. They are just the prefactor, the numerical prefactor, that takes the polarization into the output of the detector. So this is a picture. In color code, you see blue is -1, so it's maximus, minus maximum. Red is plus maximum, and green is zero-ish. So this is the response of the output of the detector to a source in this position, to the LIGO Hanford, to the sorry, this is LIGO Livingston, LIGO Hanford detector, or Virgo. But what is nicer to represent is the square root, the quadratic sum of the two. This is more physical. So look at what happens to the output of the detector. So the LIGO detector in Hanford will have 4 blind spots. You remember, no? The interferometer are two arms at 45 degrees, and it measure a differential motion of the mirrors. But if the wave arrives exactly at 45 degrees in the plane of the interferometer, it will give no differential motion just because the mirror will see a symmetric, will see basically the same, will be affected in the same way. So the detector is almost omnidirectional, but it has 4 blind spots corresponding to the 4 direction at 45 degrees in the plane in the interferometer. So you see the two LIGOs are oriented so that the 4 blind spots are basically the same. Okay, whereas Virgo, which is a few thousand kilometers away, is oriented in a different way. So it's oriented differently, so the plane is a different one. So the 4 blind spots are completely off. There is some slight superposition of the blind spot around here, but otherwise the blind spots of Virgo are different. But that also means for a given source, say a point here, the response of the two LIGO, basically the two polarization seen by the two LIGO are weighted by this roughly the same number, but they are weighted by a completely different number by Virgo. And the same will be true for Cagra or for any other detector. So only the two LIGOs are oriented the same way. Whatever other detector you add, unless you really tune to be oriented in the same way as the LIGO, which is not always possible because the other detector must be on the surface of the Earth, so it might not be able to orient in the same way. So you're observing a different polarization, a different combination of a plus and a cross. Okay, and this is a crash course recap, a very short recap of gravitational wave radiation emission from a binary. So what is the source? The source of the gravitational wave is a quadrupole. You see, this is the density of the source, the second moment, and then you take out the trace. So the second moment of the mass distribution is a quadrupole, but it's not enough because the Earth has a quadrupole too, right? And the Earth is not exactly spherical. It has some quadrupole. You need a time-varying quadrupole so that the gravitational wave perturbation, it's dimensionless. Here you have mass times length square. You multiply by g Newton, so it's a length cube. You have 1 over the distance, which is the standard decrease with the distance, and then you have two derivatives basically to match dimensions, no? Because this has to be dimensionless. Speed of light is always 1. And so you immediately realize that the source of the gravitational wave perturbation is the kinetic energy of the source, not the rest mass. No? The source of the Newtonian potential is the rest mass of the source. The source of gravitational perturbation is the kinetic energy of the source. Okay, so for instance, for a binary system will be the symmetric mass ratio times the total mass times v squared. But then you might think, well, but how is it possible that we barely, I mean, we don't see, we cannot even think of measuring the Newtonian potential of any object outside the solar system, okay? If you think of measuring the Newtonian potential of any object outside the solar system, and how is it possible that we measured something that is even smaller than the Newtonian potential outside our galaxy? Well, it's because of the time behavior. Because if you want to measure something static, then forget it. I mean, you have too much noise. I mean, the gravitational perturbation for the field of the Earth is 10 to the minus 9-ish here. So forget measuring something 10 order of magnitude smaller than that, if it has this in the same frequency band. But the nice thing is that this thing oscillate with a typical pattern, so you can go and look for a typical pattern well below the noise floor, just because you're looking a specific pattern. Okay, then you must have heard this already, no? The typical frequencies, they scale with the mass and the distance. Of course, the larger the distance between the two objects, the smaller the frequency, and at the end of the day, the distance is the same order of the mass, so the peak frequency of the gravitational wave from a binary system scales as the inverse of the mass, okay? The frequency. And the amplitude, of course, raises with the mass at a given distance, but the peak frequency decrease with the mass, because a higher mass means a bigger object, and so it takes longer to go around, so the frequency goes smaller. So you cannot really expect anything beyond the 10 kilohertz, actually beyond a few kilohertz for solar mass system, which are the only ones we know that can that are compact. Okay, because of course you can have masses smaller than this, like Earth is smaller than the solar mass, but Earth is not compact. To have a compact object of the size of kilometer, you must stuff at least one solar mass to build a neutron star, basically. And the velocity at which these two objects smash in the final stage of the inspiral is really relativistic. So nature has kind of provided us with an accelerator of black holes, an accelerator of neutron stars. Luckily, we didn't have to build an accelerator for a solar mass object, because this system exists in nature already. So we really reach relativistic velocity. Okay, then an important factor from the phenomenology is the prefactor here in front, which is dimensionless, that is related to the angle between the viewing direction and the angular momentum of the object. So if we look at the system from the top or from the side of the plane of the orbit, there is a modulation factor. You see, for instance, the plus polarization, for the plus polarization, this modulation factor is never 0. For the cross polarization, it can go to 0. But in general, we never miss all of the gravitational radiation if you look from a kind of unlucky angle. Okay, but we can miss more than half of it. So if you are very lucky, we have theta equal to 0. We see the two polarization with maximal intensity. And if you are unlucky, we see only 1/2 of the plus polarization and nothing of the cross polarization. This has nothing to do with the localization of the detector on the Earth. No? All detectors on the Earth will see the same theta, because it has to do with the viewing direction and the orientation of the binary. And of course, the source is so far away that if I look it from here or from there, the angle, the viewing direction is exactly the same, no? Because the detector are a few thousand kilometers apart, whereas the source is 100 of megaparsec away, okay? Megaparsec is 10 to the 19 kilometers, so the source is basically at infinity, and this parallax is impossible to measure. So this theta is the same for all the detectors. Only to do with the angle between the viewing direction and the orientation of the plane of the orbit. Okay, but there is another very important thing here that has consequences for cosmology. Look at this phase, Irene already talked to you about match filtering. And so what we go when we analyze the data, we really look for pattern in the oscillation of this phase. This phase is not an exact cosinus, but is a cosinus with its changing frequency, and it's exactly this changing frequency that we detect and give us a lot of information about the source. So this phase is dimensionless, so it depends on time. It cannot depend really on time. It must depend on time divided by something that kills the dimension. And the only thing we have mass. So time divided by mass is dimensionless, right? Yes? As you, because there is G Newton, okay? Here I didn't write G Newton, but G Newton is a converter between mass and length. Of course, length and time are the same thing, because the speed of light is equal to 1. So mass is actually a length, because G Newton in this formula is equal to 1. So it cannot depend on time, but it cannot depend on time divided by mass. Of course, the astrophysical source has other dimensionless parameter. Well, just as a start, it has two masses, not one mass. But okay, let's take the total mass and let's trade the other mass as a symmetric mass ratio. So the other parameter is dimensionless. So it's dimensionless, so the phase can depend on this symmetric mass ratio alone. So we take only one dimensionful parameter, total mass, then the symmetric mass ratio, and then the spins. The spins has dimension two, but they are mass, time length, time velocity. Spins are angular momentum. Mass, time length, time velocity. Velocity has no dimension. Mass and length is the same dimension, so a spin square divided by mass to the fourth is also dimensionless. No? Okay, so these are another dimensional factor. The only dimension, the object with dimension is mass, so it has to depend on time divided by mass. But be careful. So you always heard about talking about redshift. Here, all these sources are extragalactic sources, so we better take into account redshift. So the time evolution, the time that dictates the evolution of the source is not the time of us who observe. There is a redshift between the two. So when we express the source time in terms of the observer time, we get a 1 plus z, just the standard redshift. And so what we fit from the shape of the phasing of the gravitational radiation is not the intrinsic mass of the object, but it's the so-called detector mass. It's the intrinsic mass shifted by 1 plus z. Okay? So we better rewrite the amplitude as a function of the measured quantity, mass times 1 plus z. So at the denominator, we don't have any longer the distance, but rather the distance times 1 plus z, just to compensate this, that we arbitrarily put it to express the amplitude in terms of the mass that we fit from the data. And so we call it this Carly M, and then in the denominator we get luminosity distance. And so what we measure is all these intrinsic parameters are measured by looking very carefully at the specific shape of the phasing. And then you get the amplitude. And then the amplitude, this is fixed. This is already fixed because you measure the phasing. From the amplitude, you get this combination of distance and angles. And this combination of distance and angles. So if you have an independent measure of the two polarization, then you measure with two measure. We measure H plus and H cross. And so you measure theta and distance. If you measure only one combination on the two polarization, then there is a degeneracy. You will never measure distance and the angle. You measure a combination of the two. So that's the source of the big error in the luminosity distance measure that you've seen with LIGO so far. So unless you happen to measure the two polarization independently, and so you can disentangle distance and theta, you are bound to have a large error on this because of this degeneracy. Okay, so all of this was basically gravitational wave 101. Okay, you have seen this already, but let me show it again because it's so beautiful. I mean, 10 years ago, people would, I mean, astrophysicists would have given, I don't know, 1 year of their salary to have this. But now we have it for free. Okay, so these are all, each detection is 3 black holes, or I mean, 3 compact objects. I mean, you see these are binary neutron star giving rise to a possibly black hole, we don't know. These are a mixed system of binary neutron, black hole neutron star. This we don't know because if it's a mixed system of a black hole and a neutron star, then that's the heaviest neutron star we've ever seen. If it's a mixed system of a black hole with a black hole, then that's the lightest black hole we've ever seen. So this poses a problem if we measure the mass of this object correctly. And you see, basically we see the bulk of the black holes, they happen to have a mass of 20, 30 solar masses, which was not really expected 5 years ago, I mean 8 years ago, before we started to see this object, because what, I mean, we hardly see black holes of solar mass outside our galaxy, okay? Because black holes of solar mass, they are not huge gravitation, electromagnetic emitters. Actually, they are not at all electromagnetic emitters, but black holes of solar mass, they might have a companion. You know, the companion might be so kind to donate matter to the black hole, and the matter accelerated will emit light. So we see few black holes in our galaxy, which are not here, and they are slightly less massive. They are around 10-ish solar masses. I think we see 1 or 2 black holes in the next nearby galaxy, but basically all the black holes we see are from the local group. All the black holes we see electromagnetically. Whereas here, it seems to point to a kind of different population of black holes. I will come to that later. So, why we don't see black hole of masses of 200, 300, 500, 1000? Well, probably, I mean, they might not be there simply because nature was so that didn't make them. But we cannot say that because it's related to the frequency of the gravitational wave detector. The gravitational wave detector cannot see things below, here I've been a bit optimistic, actually below 20 Hertz. And so the object must not be must not be too big. And black holes of 100, 200, 300 solar masses are just too big, and their signal falls out of our detector. So we cannot say much about detectors which are, I mean, by convention, when people talk about solar masses black holes, people means from 1 to 100 solar masses. So you can say that 100 is not really 1, but okay. We 2 order of magnitude is still fine. So up to 100 solar masses, that's solar mass black hole. Beyond 100 solar masses, we are not really sensitive, so it would be really nice to start seeing those two. Okay, if you ascribe pedantically to this definition that up to 100 solar masses is solar mass black hole, between 100 solar masses and 10 to the 5 is intermediate, and beyond 10 to the 5 is supermassive, then if you are really pedantic about this nomenclature, then this system is basically the first ever detection of an intermediate mass black hole. A black hole which is not solar mass, just because it's the remnant of 80 plus 60, and then it was 100 and something. Okay, this for the records, if you want to write a new line in the Guinness of Records. On the other hand, after this gap between 10 to the 2 and 10 to the 5-ish, then we know supermassive black holes are really popular these days, no? The Event Horizon Telescope saw a supermassive, you know, they actually took the picture of a supermassive black hole of 10 to the 9. In the center of our galaxy, there is a supermassive black hole of 10 to the 6. So supermassive black holes that reside at the center of the galaxy are not a surprise anymore. I mean, they were a surprise 20 years ago, but nowadays they are common stuff. Basically, we believe that most of the galaxy have a supermassive black hole at their center. There is just this desert between 10 to the 2 and 10 to the 5-ish that we hope to fill with future experiment. Okay, and then another curiosity is that, okay, all the black holes that we see here, we think they were formed by astrophysical collapse. That's the standard law. So there was a star, the star grew, ate a lot of gases, and then at some point it kept making nuclear reaction, burning heavier and heavier nuclei. At some point it ran out of fuel, and then it imploded. Well, but there is a problem, because at some point the stars are so massive that the pressure at their center becomes so strong that instead of triggering nuclear reaction, it can make electron-positron pairs, because the energy there is so strong that it exceeds the 1 MeV, so it can create electron-positron pairs. And so it's believed, I mean, nobody has seen really that, but stellar model believes that there should be a hole in the distribution of stars there, so the stars with that mass should just explode. So instead of ending their fuel and collapsing into black holes, the star should explode. And so this gap in the stellar mass should lead to a gap in the black hole mass. There should be no solar mass black holes in the range 60 to 80 solar masses. but we see them. Anyway, the black hole, the more massive they are, you see, the more on the left of this plot are. These are the noise sensitivity curves of real noise sensitivity curve in O1 and O3. And these are typical spectra. This is the amplitude of the spectra. So for instance, the lightest signal waves, yes, the binary neutron star, you see, you see all the in spiral, and then the signal actually ends out of the band. And then you increase the masses, the signal start to end inside the band. Then the most massive signal that we have seen with a total mass of over 100, it ends here. So this is the design sensitivity, and luckily we were not there, we were rather here. So you see, when you see higher and higher masses, the signal goes to the left. Of course it's stronger, but then you see it farther away. So basically the amplitude that arrives on the Earth is basically the same. And you see, we see very, very few cycles. So, and they have to compete more with noise. So the signal at higher mass, they hit the detector in this low frequency band are the least well measured. So before we can really say that this is a problem, we better accumulate more statistics. The problem of having 60s, 70s solar mass black holes that come from this signal that appear in a low frequency LIGO that are at odds with our expectation of black holes formed by stellar collapse, where we shouldn't have stellar collapse here. So what this has to do, okay, just another thing about observation, then I will tell you what this has to do with cosmology. So with only two detectors, like our ears, now we do triangulation to realize what is the direction in the sky. So with two detectors, the main source of information about the localization in the sky is the delay. So for instance, I have two detectors here, and the signal goes there, then I realize that this detector sees it first, this detector sees it second, so there is usually a full circle in the sky that is compatible with the delay. So these are galactic coordinates. So a circle in our sky, here corresponds to a, I call it a double banana. Maybe there is more scientific term to designate the curve, which is basically goes like this. But you see, basically no signal has a complete line like this in this sky localization. I mean, of course, there are 90 events. Here I plot you only a bunch of them. Why? Because you remember there are some directions we are blind to. So if you see a circle in the sky, but when the circle crosses a region where you're blind, well, it cannot come from that point. So instead of having a full line in this galactic coordinate projection, usually the sky localization are one banana and another banana with the disjoint. Then there are a few events that have been seen by 3 detectors, including LIGO, including Virgo, and so the sky localization shrinks to few tenths of, not tenths, but tenths of square degree. 20 square degree, 40, 100 square degree, okay, just for those lucky events. But otherwise, with 2 detectors, you are bound to have this huge sky localization. So if you're looking for kilonovae and similar, now that Virgo is not on and Cagra has very low sensitivity, I mean, you cannot expect any better than this huge 1000 square degree sky localization. I mean, that's the way it is. If you want to have better sky localization, go and donate to Virgo so they can hire more people and adjust the experiment. Okay, not you, usually students are poor, so not you specifically, but make so that people donate to Virgo. Okay, and these are the rates. So I didn't mean to offend you. I mean, students don't have money to spare usually, right? I know I've been a student for some time. Okay, and these are the rates. So the rates that we see of binary neutron star is of the order of, okay, look at the units, megaparsec cube per year, okay? So in a volume of 1 megaparsec cube per year, we now know that we have around 10 to the minus 6 events. So what is the megaparsec? I mean, I will have a slide on universe scales. So our galaxy is tens of kiloparsec. Then our neighbor galaxy is a few hundred kiloparsec. Yes, a bit less than a megaparsec. The average distance between galaxies is 5 megaparsec. Okay, so if you take a random cube in the universe, you have to take a random cube of 5 times 5 times 5, 100 megaparsec cube to have on average one galaxy. Okay, in 100 megaparsec cube in a universe, you have on average one galaxy. So that means that since this is the rate per year, so basically for a galaxy like ours, usually you have to expect 10 to the 4, 10 to the 5 years to have one event. Okay, these events are very rare compared to supernova, where you have less than a century, 50 years. These events happens every 10 to the 4, 10 to the 5 per galaxy. But why can we see relatively many of them? Well, because we can see a large distances. No, when we go, as I said, the average distance between galaxies is only 5 megaparsec. If we look at 100 megaparsec, then we see 20 to the cube galaxy. If we see to 1 gigaparsec, we see 200 to the cube galaxies. And so this can offset the small rate. So this is the rate of neutron stars. This is the rate of binary black hole. You see, binary black hole rate is smaller. It's even less than 1 per million. But we see many more binary black hole. Again, this has to do with the reach. Binary neutron stars are small mass, so we can see them up to 150-ish megaparsec. Black holes can have arbitrarily large mass. Actually, the distance range of them is limited by the fact that they fall out of the spectrum. No? As I told you, when they get so big, they get so fat that it takes so long to go around each other that the frequency go low, falls outside, fall outside here for masses above a few hundred solar masses. Okay, but in general, we can see them up to gigaparsec if they are few 30, 40 solar masses. So despite per galaxy, or per megaparsec cube, the rate is 1 or 2 order of magnitude smaller than binary neutron star. In LIGO data, in LIGO Virgo data, we see in a ratio basically 100 to 1, roughly. In 19 detection, only 2 were binary neutron star. And then neutron star black hole, they are somehow in between. Also, notice that binary neutron mixed system are supposed to be seen less than a binary black hole of the same mass because of this eta, you see? Because this is the quadruple of the binary. The quadro depends on the reduced mass, and here I just want to write the reduced mass as a symmetric mass ratio times the total mass. This should be really the reduced mass, okay? Like in the standard Newtonian problem. And of course, for asymmetric system, this eta goes down and you pay a price. So asymmetric systems are not really the most likely objects seen by LIGO, so LIGO and Virgo. So you see the really prototypical objects are equal masses and large masses. Again, not too large because they fall out of the spectrum, but with some range. Okay, so this you have already seen this, but I want just to make you pay attention to this change of slope. So in O1 and O2, we have seen few detection per month, and then all of a sudden the slope of detection increased. This is not because the detector has massively increased the sensitivity. On the contrary, O3 was slightly worse than O2, but because Virgo joined. So, and one detector joins, even if he doesn't have the sensitivity to give a lot of information, still the fact that he sees a little bit of event in coincidence with the other, it increases a lot the significance. Okay, so here I don't have time. I mean, I might have the time, but I didn't prepare the slide, so I pretend that I didn't have time to explain that. At the end, when you see things in the data of LIGO or Virgo, now you see just a blip at some point. But blips can happen for any reason, like Irene told you. So what you have to do, you have to compare with the background. You see the coincidences when you shift the data for some large delay, for like 1 second, 2 seconds. You don't expect astrophysical coincidence to be delayed by more than milliseconds between the detectors. And so you count the background. And then you compare with the foreground as 0 delay. And of course, having a third detector in and see something in the third detector consistent with those pattern functions that I told you earlier about allows to boost the significance of a blip that you see in the data. So basically, that means that the background that you have in triple coincidence is much, much smaller than the background you have with double coincidence. And so when you compare your foreground, your signal, with the background of 3 detector, is much easier to say, okay, this was a signal, than when you compare your foreground with the background of 2 detector. So that's why another reason why it's important to have as many detectors as possible. Sky localization and lower the background so you can pull up more events. So now we are here, we're at the start of O4, so Virgo didn't make it, it's not active now. and Kagra is not really doing science. They are really in engineering runs because their horizon is so small, megaparsec, they don't really expect to see anything. But anyway, some point in '04 Virgo will join, and then after there will be 20 months of data, so plenty of binary black hole. And then after 2 years gap, there will be '05, and '05 should be the end of second generation detector. So in 2028, by then you should have finished your PhD. So that will be the end of second generation detector. There will be a huge gap to 2.5 generation detector. And then hopefully in 10 years when you will be professors, then there will be the third generation detector, like Einstein telescope. And so all of this well before your retirement age. So it's good to invest your time in this. Actually, it's even before my retirement age, so even more for you. Okay. So this is, by the way, not all of you have to be professor. You can there are many other things to do in life than being professor in academia, of course. So this is the reach of second generation, this is the reach of third generation detector, and this is in redshift. So you see, we barely reach redshift 1. So for very massive binary black holes, we can reach a few gigaparsec, we correspond to redshift 1. But with the third generation detector, we start really reaching, crazy. Right, I mean, redshift 100, we don't really expect to have sources at that redshift, because compact objects, they take time to form, to find a partner, and and to coalesce. So we really expect to see basically all of them. And this is LISA. LISA is same idea of an interferometer, but go to space. If you go to space, you're not bothered by this 10 Hertz boundary on your noise, because the 10 Hertz boundary in your noise is due to seismic vibration. Seismic doesn't necessarily mean earthquake. There are seismic vibration all the time, like now, because I jumped. And actually, if the detector was, in the institute, and I jumped here, the detector would measure it. Actually, in Virgo, they see Virgo is 15 kilometers from the seaside, from the Mediterranean, and they see the waves hitting the seashore. They see, it has very sharp frequency. Luckily, this frequency is around 1 Hertz, so it doesn't mess with the data, but they see the waves hitting the seashore 15 kilometers from Virgo. And there are a lot of other funny things they can see. They can see the cloud passing by, the changing the Newtonian potential because of the clouds. But again, all of these are small, low frequencies. Low frequencies for terrestrial interferometer, but that would be high frequency for LISA, because LISA is sensitive in 10 to the minus 4-ish hertz. 10 to the minus 4-ish hertz means periods of hours. Okay, so period of hours, you can even see white dwarf going around each other. You're not bound to see only black holes. And the best sensitivity of LISA will be for 10 to the 6 solar masses, but it will also be sensitive to 10 to the 3, almost 10 to the 2-ish solar masses. Okay. Okay, and this is the projection of the reach of ET. So this is for Cosmic Explorer, which is the American counterpart. You see, ET should have, it's not fixed yet, but should have arms of 10 kilometers. Cosmic Explorer should have arms of 40 kilometers. Americans, they always want to have it bigger. But the reach will be slightly larger for Cosmic Explorer. So these are what we expect to see the binary neutron star in the universe, and we'll see basically most of them. And the binary black hole in the universe, we see most of them. Why do we expect that all these coalescences happen around between redshift 1 and 2-ish? So this is the expected merger rate between 1 and 2. I mean, this is a projection that I made. There's no guarantee that it's like that. Well, it's based on the fact that we observe star formation, because star formation is accompanied by a lot of light. Okay, so we observe star formation in galaxy, and we see that it's peaked around redshift 2-ish, between 1 and 2. And so, if these objects, they come from the collapse of a star, well, you must have the star to form. You must find a partner. They must go supernova and become compact object. They must coalesce, radiate gravitational radiation. So this takes billion years. So for sure, the merger will happen later than the star formation. So if the star formation peaks around here, we convolve the star formation with a suitable distributed time delay, and we say, okay, then the merger rate must happen somewhere here. Okay, there are lots of caveats. This is just hand wave projection. And look what we are seeing with second generation detector. We are seeing this. I mean, basically nothing. With third generation detector, we'll see up to redshift 1, we basically see all of them. Then we start losing a fraction of them, but we really see most of them. And this assuming that all the binaries come from astrophysical collapse of solar massive star. If the binaries come from population tree star, the primordial star, you know, the ones that were rich in hydrogen, they were little metal, so they could grow really high in mass, then would burn really fast, then would go supernova or whatever they are called, the explosion of those 200, 300 solar masses stars, then they could be formed a redshift 10-ish, 15-ish, if those in primordial stars really play a role. Then seeing object that far, there will be a fingerprint of primordial star giving rise to black hole. But the vanilla scenario is this one. Most of the formation happens between 1 and 2 redshift, and so most of the merger must happen slightly after redshift 1. Okay, and this is a non-exclusive list of things you can do with gravitational wave research. And I don't know if you, I don't probably want to stop mentioning all of them. Yes, and let's go, and of course, multi-messenger astronomy, I put it last because I don't need to remind it to you. But, you know, you can do precision gravity because once you see the waveform carries the information about the dynamics of the source, and you know that the dynamics of the source is ruled by general relativity, so you can fit you can check the parameter of general relativity together with the astrophysical parameters. That's to say one thing. And then it's a probe of neutron star interior, because the neutron star, while they go around each other, they can start oscillating. I mean, contrary to black hole, neutron stars are made of matter, of real stuff. And the stuff feels tidal forces and can oscillate and can suck energy from the orbital motion, and you can see this oscillation, and this oscillation will be dependent on the neutron of the equational state of the matter inside the neutron star. So gravitational wave can in principle be a probe of the equational state of nuclear matter at density which are not achievable in detectors made on Earth. And then one something I'm really interested in is black hole mass function. I mean, how are the masses of this black hole distributed? I mean, this is something we don't know. It will be super important to understand. I mean, because that will give us information about the stellar mass function, no? The progenitor star, where they're distributed. So how many of them ended up into black holes? How many of them ended up in the range to give rise to planetary system? Who knows? There are a lot of things you can do. And you can do cosmology. I don't think I put here down cosmology because cosmology is the topic of the next slide. Yes, let's go to the next slide. Okay, I promise you to give you an overview of the distances which are at stake. Okay, so on the Earth, we always talk about 1,000 kilometer scale, okay? Like the distance between the detectors is order of 1,000 kilometers. Then when you move to the solar system, you start talking about few billion of kilometers or tens of billions of kilometers, no? The size of the solar system. And then you stop talking about kilometers because it's not convenient enough. You have to put too many digits in the exponent. So you start talking about parsec, okay? So you make a jump of 10 million and you get to 15 kiloparsec, which is roughly the size of the visible part of our galaxy. The Milky Way has a size of 15 kiloparsec. Then we know that the size of the galaxy is actually a bit bigger because there is a halo of dark matter, then it can reach order of 100-ish of kiloparsec. And then there is the distance to the next galaxy. So for us, the next galaxy is a bit less than 1 megaparsec, but of course, the nearest galaxy is closer than the average distance of galaxy, no? Which I already told you is 5 megaparsec. And then you skip a factor of 10 to the 3, then you reach few gigaparsec, which is roughly the size of the visible universe. Okay, and these are the conversion unit. Also in that year, if you like. Okay, so how cosmology has to deal with all of this? Well, so we start with the first Freeman-Robertson-Walker equation. Okay, I assume you all have seen it. If this is the first place you've seen it, then I'm sorry for you, because this is, it's ultra important in physics, and everybody should know it, even people who do, I don't know, condensed matter, or, it's very beautiful and very important, so there is no, and look at how small it is, how nice and compact. It's impossible not to love it. Okay, So this is the scale. We parameterize the expansion, the metric. Okay, this is unperturbed Freeman-Robinson Walker. So we parameterize the metric as you see, time times an expanding space. And then instead of when you talk about astrophysics or cosmology, rather than talking about the scale factor at a definite time, you rather talk about redshift. With the convention, the redshift today is 0. So, and the redshift at an earlier time must be larger than 0, because A is always smaller than 1. Since the scale factor is 1 by definition today, then it must have been smaller in the past, because, I mean, by now we know that the universe is expanding. No? Okay, since 70 years, 60 years, we have no more doubt about it. Okay, so the distance of an object, since whatever we see from an object is carried by light or gravitational wave, which move at the speed of light, if you set this equal to 0 and you try to get the coordinate distance relative to this object, well, you can trace it to the time that it has spent traveling that photon. So you play a little bit with the, you see, delta t squared is equal to a squared delta x squared. Then delta x is equal to delta t over a. Then I play with the differential. Since a is a dot is dA in dt. You see, dA and dA simplify. The dt recovers the original dt. A and a square recover the original a. So basically, all of this combination is nicely expressed as an integral over redshift of h of z. You see, since the density, of course, is changing with time, so in changing with redshift, in changing with the scale factor, h is also changing with the scale factor. So basically, the distance at which we see object depends on the expansion rate of the universe. So electromagnetically, we usually measure luminosity distances, which are ratio between the energy rate emitted by the source and the flux that reaches us. So we can measure luminosity distance, A, if we have a detector detecting some flux, and B, if we know the intrinsic energy rate emitted by the source. No? Like for supernova, somebody knows how to, I mean, not me, but somebody knows how to calibrate them. So you know the E dot of the source, you know what reaches your detector, so you can know the luminosity distance of that object. Luminosity distance is just this coordinate distance times 1 plus z, so you just plug in 1 plus z in this formula, and then you trade h for the Freeman-Robinson equation, and then you remember that rho is made of different components. So in practice, a small redshift, only two components matter: the cosmological constant, that redshift in this way, and matter, the redshift in this way. And this omega matter are just the fraction today of matter of energy density in matter in cosmological constant. We know that today this is roughly 0.3 and this is roughly 0.7. Okay, so this is the exact formula, I mean, with the approximation that I told you, that we look at only two components, we look at small redshift, and you really look at small redshift. This z you can neglect, this z, this is integral of 0 to z, this is just delta z times 1 over h0. Because it's small redshift, you neglect all the z here. Oh, sorry, this should be a z prime. You neglect this, this is 1, and so this gives you just z. So this is the standard redshift luminosity distance relationship. Then you can complete with a higher order. So the idea is that you do it with supernovae, but you can do it with gravitational waves, because we measure luminosity distance. We want to infer h naught. We just miss z. But gravitational waves, do they give you z? No. Okay, you know that. You remember, gravitational waves do not, because we measure the reshifting mass, but we don't know the intrinsic mass. And so the reshifting mass enter also the amplitude, so we measure luminosity distance. We don't have a handle to measure redshift. I mean, you might be able to measure redshift in some specific case, but no. Okay? So the idea is that we need something that gives us redshift, and typically it's an electromagnetic counterpart. But again, most of the objects we see are black holes, and black holes do not emit light by definition, more or less by definition. Of course, if they have some stuff around them, but this is not AGNs, which are huge, million, billion star AGN, which is sucking a lot of gas. These are kilometer-sized black holes, 10 kilometer-sized black holes, 50 kilometer-sized black holes. You don't expect to be much matter around them, okay? So you need for something else that gives you electromagnetic counterpart. Or you can say, well, after all, these black holes must be in galaxies. For galaxies, I kind of know their evolution. I kind of know the star formation rate. I can infer statistically the average properties from the average property of the galaxy population, how much binary black hole merge. And so I can think of, on average, I can do a statistical inference of how many assuming some quantitative shape for the distribution of merger of black hole in redshift space. But then, of course, if you want to do this, you better have thousands or tens of thousands of detection, which, by the way, third generation is going to provide us with. Okay, and so this is the results we have so far. So the pink line is the determination of the Hubble constant by CMB, the green line by supernova. The two do not match. There are quite a lot of different assumptions in the two. So yes, we are surprised that they do not match, but there is a lot of room for systematics in either of the two. Or might simply be that, so the CMB come from physics at Z order 10 to the 3, the supernova come from physics at Z less than 1, and the black curve is the determination of the Hubble constant from the only one event, that gravitational wave event that had electromagnetic counterpart, only one, the binary neutron star in August 17. And you see, the error is large because it was seen mostly by the two LIGO. Virgo was on, it helped in sky localization, but couldn't help much in measuring the two polarizations separately. So you remember, if you don't measure the two polarizations separately, you're bound to have a large degeneracy between the distance and the angle of the plane of the binary. So we don't really know if we saw something a bit farther away, but with very good inclination, or something a bit closer with a slightly worse inclination. We cannot know. We probably think that the inclination was not optimal because the GRB was not very strong. So we must have seen the GRB off axis, so the inclination must not have been optimal. But still, you cannot escape this huge error. You see, from 50 to over 120 is all possible. But then what can you do? Wait, all the binary black holes, are we sure we have to throw them into the bin? Can we do something with these binary black holes? Oh, what can you do? We don't have redshift. Well, but we have sky localization, no? To some amount. Not for all them, but for some binary black hole, we have a sky localization which is not too crappy. So what one can do is look at the sky localization, take all the redshift of all the galaxies there, and by the way, this was the original idea by Schutz, no? Irene, I think, has told you about it. And say, okay, we take all the redshift for those, and we join the information of the binary black hole with the binary neutron star with counterpart. Of course, each binary black hole has way less information than one binary neutron star with counterpart. But binary black hole, we have a ratio of 50 to 1 to binary neutron star with counterpart. Actually, almost 100 to 1. So maybe accumulating statistic might be competing to one event with huge information. Okay, for the moment things are not ultra promising, just because we move from the black curve to the orange curve. And you see we have an orange curve and you have a dot curve. They correspond to assuming two different mass distribution for the black hole. So you see, once you start to degrade using the events that individually has way less information, then you have to make assumptions. And basically astrophysics, that was out of the door, it comes from the window, because astrophysics has to tell you what is the mass distribution of your black hole, and that affects a little bit the estimation of the cosmological estimation from the dark sirens. This was the bright sirens, the black hole. Bright sirens, you have redshift, you have luminosity distance with big error, but you have luminosity distance, and you get this curve. From this, if you fold in the information from dark sirens, so binary black hole for which you don't have redshift, but you have some sky localization. You take all the redshift for all the galaxies there. You see, the error box shrinks a little bit, not substantially, but a little bit. The problem is that you cannot take all binary black holes, those happening in a gigaparsec away, with basically localized enough of the sky. That wouldn't help. You have to take the binary black hole which are sufficiently close by so that the sky localization does not encompass zillions of galaxies. Okay. Okay, and this is a projection for the future in this paper. So this is what happens with the error, the precision in a Hubble scale if you accumulate 20, 30, 40, 100 detection, all of them with the electromagnetic counterpart. So for 100 detection with electromagnetic counterpart, then you measure H naught with less than 2% precision. But this is a dream. I mean, most of our detection are without electromagnetic counterpart. So if you use sky localization from binary black hole and use galaxy catalog, which are 100% complete, so we are sure that out of the many galaxies we pick, there is always the good one. Well, our precision will degrade, but a factor of 3-ish, not too much. But again, the galaxy catalogs are not very complete beyond 200 megaparsec. At the moment, LST can change the business. So you have to account for the fact that out of all the galaxies that you pick in your sky localization, the good one might not be there. So if you say that the galaxy catalog is 75% complete, 50% complete, 25% complete, of course the error degrades. I mean, the error increases. I mean, you cannot have all of them if you don't fold in the information at the beginning. So this is a kind of projection. So now we are basically here with the error of we have one. I mean, this plot start with 10 detection with electromagnetic counterpart. No, we are one detection with electromagnetic counterpart and 10 binary black hole with some reasonable sky localization and with galaxy catalog which are reasonably complete, but not 100% complete the distance. And then again, the complete galaxy catalog change drastically with the distance of the event. I mean, a gigaparsec, forget it. At 200 megaparsec, I mean, we can discuss. Okay, and this is another prediction of the same thing. I mean, how the error in the Hubble constant shrink as we accumulate events. This was done for galaxy catalog 100% complete. But this paper was already in 2011, just to tell you this is not a new idea. Actually, it was Schultz's idea from the 80s implemented here. Okay, and I think I should wrap up, right? No? Yes, okay, but I'm wrapping up anyway, because I'm tired and I want to listen to your voice. I mean, you see. Okay, what is important? One take-home message that you should all remember. So even if you decouple from me, just come back now. Hey, hello, come back now, because this is important information you have to carry with you and never forget in your life, even if you go to work in a bank afterwards. Look at this. This is the frequency change of the gravitational wave signal. Okay. So of course there is the coalescence, so frequency is sweeping up, okay? Frequency is increasing, and then the system is going down because the energy is negative, okay? The velocity is increasing, the system is accelerating, but the total energy of the system is minus the kinetic energy. No, it's kinetic energy plus potential energy. Potential energy is minus twice the kinetic energy, so the energy is going down because it's negative, but in modulus is going up. So frequency is going up, and you see, again, I like to play with the differential. No? I did it before, so I do it here. dF in dt is like E dot, so the energy emission rate, divided by how the energy depends on the frequency of circular orbit. Okay, so d simplified, dF goes up, and I have dF in dt. So this is a mathematical identity. I guess mathematician here would be horrified by my use of differential, but we know it's correct, right? I mean, we are physicists. We know it's correct. So this is dE in dF. I do dE in dV. As I told you, energy is minus the kinetic energy. Let's forget about the minus. So it's reduced mass times V square, 1/2 reduced mass times V square. I derive with respect to V, so it gives me this, and then I do dF in dV to compensate that. And this is the quadruple formula. I guess, Irene must have shown you, is symmetric mass ratio square times V to the 10. And funnily enough, E dot is dimensionless, because mass is length, G Newton is equal to 1. Mass is length, so the in dt is dimensionless. So that's why you can guess that the quadruple formula must give you eta squared because it's reduced mass square, The quadruple square, each quadruple gives one symmetric mass ratio. V to the 10, well, the 10 you cannot guess. You have to do the computation. But some power of V is for sure because it has to be dimensionless. So if you plug in the Kepler's law that tells you that the velocity goes as f to the 1/3, or velocity cube is linear in f, this is just Kepler's law, r cube over t square is equal to the mass. Then you get this behavior. You get that 1 power of eta the power of the mass to the 5/3. No, this funny 1/3 comes from when you replace velocity with frequency, and then just for dimensional reason, once you know that the mass is 5/3, the frequency must be 11/3, just to give a time square. No, this is f dot, which is time square, so this must be time square. And then, of course, this is formula based on Newtonian physics. Then, if you want to add post-Newtonian physics, then you have correction in v squared. The correction will depend on the symmetric mass ratio, but not on the total mass, because the total mass has dimension. So, since this is already the right dimension, this cannot depend on the total mass. Okay? So, you have this formula. So, this tells you immediately one thing. When we look at the phasing, how the phase is changing with time, what we can measure very accurately is this combination, eta times mass to the 5/3. Or if you want to trade it for an object that has the dimension of the mass, is eta to the 3/5 time mass. Eta to the 3/5 time mass is something that we measure very accurately due to the change of the frequency. And then because of this additional dependence on the post-Newtonian parameter on eta, then we can measure also eta separately for this combination eta mass to the 5/3. So this is the inference of the, you see, these are all the 90 events. So this is the PDFs of all the shear masses of all of them. Of course, the mass we observe are not completely representative of the masses of the sources, okay? Because when we look far away, we only see the most massive object. We don't see all of them. So, since we see roughly same quantities of more massive and least massive, the least massive must be intrinsically higher. So when you translate the observed distribution to the intrinsic distribution of M1, say, then you see that the distribution should be this. So peaked around 10 solar masses, which is okay with what we expect from stellar collapse. Stellar collapse should give rise to black holes above 5 solar masses. That's fine. And then the distribution should go down. But there is a surplus of objects around 30 solar masses. This is the thing that people was seeing in kind of surprise, because of course, when it's like, when you travel the first time, you think that everywhere is like at home, no? Okay, and then you're surprised. Oh, but here they do things differently, no? Like for instance, here they cook pasta very differently from Italy, but don't tell them. Okay, but then you see, okay, we are in the Milky Way. We know that we have black holes of 10 solar masses. I mean, that's what we expect in all galaxies, right? No, I mean there is this peak of 30 solar masses black hole that we are not expecting. But I mean, why all the galaxies has to be like the Milky Way? So apparently the Milky Way happens to be a galaxy with slightly large metallicity than the galaxy we are seeing with binary black holes, okay, with the gravitational waves. With gravitational wave, we are seeing the more massive black holes, and the more massive black holes are more likely to be formed by a galaxy with small metallicity. Yeah, you are all with me with that, yes. Because why? Small metallicity means that the star that was the progenitor was made basically of hydrogen. Okay, and if you have only hydrogen, you don't have, I mean, I'm not originally an astronomer. You probably are. So whatever is more massive than the nucleus of hydrogen is metal. So if you have a heavy nucleus, an heavy atom, it has a lot of absorption lines. So a star which is collecting heavy atoms, while emits radiation, it can make a lot of anelastic. The light emitted by the star can have a lot of anelastic encounter with this gas and strip a lot of gas. And so the star will happen to be more lighter, like our sun. If on the other end it's only hydrogen and helium, you have few absorption lines, so the light of the nuclear reaction will go through and the star will be massive. So it might just simply happen that we are selecting galaxies with low metallicity with higher massive black holes. But they don't seem to be the bulk. You see, there seems to be a superposition of two populations. Again, these are huge errors. We need to accumulate more statistics, because you see here we are fitting all together at once, because the distance and the masses, and this is the distribution, the intrinsic distribution of mass ratio 1/2. Again, mass ratio equal to 1 and 1 equal to M2 is favored by observation because it gives a stronger signal. But even that, it seems to see that the binaries prefer to be formed on democratic basis with two partners of roughly the same mass. And this is important, as I told you, when you want to do inference with black silence. And then you can say, well, but okay, this is also the measure of the rate we can do today. You see the measure of, so at very, very low redshift, we don't have events, so the error is a bit bigger. Then it shrink a little bit when you start having events. Then again, it get bigger for larger redshift. And the black curve is the star formation rate. So we know that if, it's a big if, but it's an if that we kind of accept, all the black holes, all the compact objects come from the collapse of solar masses object or solar masses stars, then the merger rate must be to the left of the star formation rate. So for the moment, the error is so huge that, I mean, it could be well on the top of the star formation rate, or could happen even before the star formation rate, of course. We don't expect that. But hopefully, now, accumulating more and more detection, we'll be able to shrink this error bar and say, oh, wait, the merger really happens, say, on this curve, which is after the star formation rate. Or, surprise, if we see that the rate we measure happens earlier than the star formation rate, then it means that there is a significant contribution to the compact object from unusual objects that were not late star, but must be primordial stars that were formed before that z equal to 2 peak of star formation. Okay, and this if you want to do cosmology with, this is too much stuff now. Okay. What you want to, okay, here I'm plotting again this. The idea is that what you can do, you can fold in also the information of the expected distribution of merger, but then of course you have to make a lot of assumption on how the star formation rate is translated into merger rates. So basically you introduce some extra parameter that you want to fit along with the cosmological parameter, so that will degrade your precision. So for instance, we made the simulation of how well you can measure H naught if you have, say, 10,000 detections, or 40,000 detection. You see 40,000 detection, and you don't assume a galaxy catalog, you don't assume electromagnetic counterpart, you only assume that you know with some uncertainty the primordial distribution of merger rate, and then you fit together the cosmological parameter and the primordial distribution of merger rate, and then you see the error keeps being large even with the 40,000 detection, but show that this kind of fit is not impossible. Of course, it has huge error because you have to fit a lot of things together, but this is to say that there is a kind of hierarchy. I mean, electromagnetic bundle needs to start with electromagnetic counter. Okay, we're all happy. We know the redshift, we know the distance, we take one fraction, even a 6-year-old student can do that, and you measure H naught. We don't see the electromagnetic counterpart, we have to use galaxy catalog. Okay, that's a bit more complicated. You must have access to the galaxy catalog, do the Bayesian inference correctly, or you can do something even more far-fetched, use just the fundamental distribution of stars, trade it for a distribution of merger rate, and this is the projection with tens of thousands of detection. But third generation detector will take us there. We will have tens of thousands of detection per year, even more. Actually, we don't know exactly how many, but the ballpark is tens of thousands, maybe even 100,000 per year. Okay, then this is a fun fact, just a fun fact. You see, the the amplitude of the gravitational wave depends, when you go to Fourier space, depends on the mass to the 5/6 times frequency to the -7/6. Okay, the fun fact is not this, but let me explain this first. So the amplitude of the gravitational wave in Fourier space is the dimension of time, okay? So it has to go as 1 over d, 1 over the distance, and this dependence comes from the stationary phase approximation. I think it was done in the Rena's lecture. And so at the end of the day, here must have the dimension of time. You can only have mass to the 5/6 to have the right dimension. Look at what happens. When you go to higher redshift, the luminosity distance goes as the coordinate distance times 1 plus z. The measured mass goes as the mass times 1 plus z. Since this is to the power of 5/6, basically the redshift dependence in the amplitude basically drops. So it's not true that when you put your object farther away, the amplitude decreases. I mean, it's not true because it decreases 1 plus z to the -1/6. 1 plus z minus 1/6 is always 1. Okay? So it's not true that if you put a farther redshift, its amplitude decreases. Okay? It decreases only 1 plus z to the -1/6, which is very mild. But it's true that the signal to noise ratio in your detector decreases. Why? Because of this. Because if you put a larger distance, the detected mass goes higher, so the signal moves to lower and lower frequency, so it tends to fall out of the detector band, so the signal to noise ratio actually diminish. So if you go to large distance, the signal to noise ratio doesn't diminish because you are at large distances, no, because there is almost compensating factor in the numerator, but it diminishes because is falling off the detector band. Okay, this is just a fun fact for you to know. Of course, this is true when z is larger than 1, okay? When z is smaller than 1, you don't see this effect. You just see the increasing on the co-moving distance. But you see, this is the co-moving distance as it increases with redshift. Basically, it saturates. It doesn't really asymptote. It's not an asymptotos. But it saturates around 10, 12 gigaparsec. So when you really go to cosmological distance, the co-moving distance is kind of constant. This 1 plus z is kind of compensated by this, but the system follows the frequency bandwidth because it goes to small frequencies. Okay, and I stop here to take your questions.
Okay, questions up there.
Hi, Riccardo. Great talk. Thanks for the lecture. Could you go back in slide 12, please?
Slide?
12.
Yes.
Let me see. The point, understanding the life of a pulsar and its evolution.
Yes.
Could you comment a little bit more about this?
Okay, yes, this is not my beach, no è mia praia, as they say. But, you know, a pulsar, an isolated pulsar, not a binary, isolated pulsar might still emit gravitational waves. How? If it has a mountain on it. If it's not perfectly spherical, if it has a little mountain on it, its ellipticity, you know, will make so that it will have a quadruple. And so when all pulsars are rotating, otherwise we wouldn't see them as pulsar. When it rotates, this would emit a gravitational wave. Of course, this is way smaller amplitude than, you know, two binary black hole, because there the quadruple is really given by the whole of the mass going around. There the quadruple is given just by the small mountains. So we are in principle sensitive to this object only within our galaxy, but there are thousands of pulsars in a galaxy. The problem is that we haven't seen, I mean, we know pulsar electromagnetically. We try to see the signal of gravitational wave from them, but we haven't seen any. So this puts only bounds on the degree of ellipticity they can have. I think now the bound, the more stringent bound is around 10 to the minus 6. So, you know, a neutron star isolated pulsar has a radius of 10 kilometers, and we are saying that it is more spherical than 10 to the minus 6, so 1 kilometer is 1 millimeter. Yes. So if it has a mountain, it must be smaller than 1 millimeter, otherwise we would have seen it. This is for the nearest pulsar. Of course, if the pulsar is farther away, then the bound cannot be so stringent. So if we would see them, then we would understand how unspherical they are. So we would teach something about the equation of state. Maybe we could teach how they got there, about their evolution. So individual isolated pulsar, not binary, isolated neutron star, they are endless source of information. Once we see them, we haven't seen them gravitationally.
Okay, thanks.
Oh, hey, okay, AJ.
Thanks for wonderful lecture. I have a question, not from your slides, but I just want to know, do gravitational wave from distinct event can interfere like electromagnetic waves?
Yes, but you have to remind that it's something fundamentally different here. No? An electromagnetic detector measures the intensity of light. Why? Because the source, whatever source you're looking at, has zillions of fundamental emitters. Okay, emitters of light are atoms, and the star, an astrophysical object, is made of not zillions, but zillions of fundamental sources. So their electric fields are incoherent one with the other. So what you can hope to see is just the superposition of the electric field that gives you the intensity. Okay? Forget measuring individual electric field of individual sources. For gravitational wave, it's completely different, because the coalescing binary, you know, you have a coherent motion. You have one solar mass, so you make the count of the number of atoms, they move coherently. So if you want to make the parallel with electromagnetic, it's like if all the atoms were emitting the magnetic field coherently, which of course is impossible in electromagnetic, but it's what's happening in gravitation. In gravitation, all single components of the star or the black hole are emitting gravitational wave coherently. That's why we see the amplitude and not the energy, because the energy would be, forget it. Okay? And that's why our signal goes down as 1 over the distance. So since we see the amplitude, the interference is trivial. It's just the sum of the amplitude. And indeed, with third generation detector, when the rate of the event will be several per days, we'll see things superimposed. Yes, we'll see one amplitude on the top of each other, but will be a different interference than in electromagnetic case, where you have the mixed product, no? Because if you have E1 plus E2, and you only measure the total electric field square, you have E1 square plus E2 square plus 2 E1, E2. That's what you usually call interference in electromagnetism or in quantum mechanics. In gravitational wave, we see the interference because we see H1 plus H2. I mean, there's no mix there. We see the sum of the two. So the problem would be another one, would be that if one of the two signals is much louder than the other, for instance, so we better model the first one very well, because if we subtract the first one, but we subtract it wrongly because our modeling is not very good, we are polluting the second signal, and we screw up the parameter estimation of the second signal. So this will be the problem of interference in gravitational wave, which is completely different from interference in electromagnetic waves. Okay?
Yeah, thank you.
Okay, we have plenty of time for questions, so.
Hi, thank you for the lecture. To estimate the redshift, you said you could use the electromagnetic counterpart or the galaxy catalog statistics. How exactly does this work?
I mean, if you know galaxies and you know their sky localization, so you cross correlate, LIGO Virgo tells you, okay, you are there, and you say, you just count all the galaxies which are there. And then you can say, well, galaxies are not actually distributed like the average distribution, okay? Like we are less than a megaparsec away from our nearest neighbor. We are not 5 megaparsec as the average should tell you. So you use the information that galaxies are not only distributed as the average, but they're really clustered. So even if you don't see, even there might be some galaxy that you don't see because it's too faint, you assume your galaxy correlation function and you use that to infer the galaxy that would be there just based on your information on galaxy correlation. The galaxies tend to stay together, no? Because they tend to get together, then there is a vacuum, then there is a vacuum distribution, and then they tend to stay together. So on the top of the galaxy you actually see, and those, I mean, no mistake, you can use the fact that you think you know the galaxy correlation function.
Hi, can you repeat the argument of how do we estimate Z with the gravitational waves? You said that there is sky localization and then we infer from...
No, we don't estimate. I mean, please don't go out and say, oh, Riccardo told me that you can estimate Z with gravitational. No, you don't. You don't estimate, never estimate Z with gravitational wave. No, we don't. There are some niche ways in which you can estimate Z with gravitational wave, but I don't want to get into that because they are, you have to make some assumption. So in principle, it's possible, but you really have to make some assumption on the sources and things. So in general, you don't estimate redshift with gravitational wave. The way you estimate redshift is by, okay, I see that the gravitational wave came from here, So I look at, and it was at 400 megaparsec, plus or minus 100 megaparsec. That's the typical error box we have. And so, okay, I ask my astronomer friend, give me all the galaxy catalog you have for that region of the sky. So first you have to be careful that if that region of the sky is not too close to the galactic plane, otherwise forget it. Okay, let's assume that this is not too close to the galactic plane. And so I count all the galaxies which are there. And I take all the redshift which are there. 400 megaparsec is a bit challenging because you don't see all the galaxies at 400 megaparsec. So there'll be holes in the catalog. But okay, I take the galaxies which are there, which are the closest or the brighter. Anyway, the brighter are the ones which have more mass, so they're more likely to host the black hole too. And then I make my inference. My inference might have a huge error for one event. The idea is that if I add up 100 events, 200 events, 1,000 events, the error will shrink. Will shrink more with dark siren, or will be competitive with a bunch of bright sirens? Well, it depends on the completeness of the catalogs, it depends on the error box of the sky localization. I mean, there's no unique answer. Since you, You don't know which is winning. Well, let's use both. Let's use bright sirens, which we have only one so far, and let's use dark sirens by cross-correlating to galaxy catalog. Also, using bright siren will really help to have the measure of the second polarization, to have another detector measuring the second polarization. That will really help. And for some time, we won't have it. So one reason more to take care of dark sirens. I mean, not to discard their information.
Okay. Thank you.
For the sensitivity plot of the detectors, yeah, you have those really big peaks.
Yes.
What do they mean?
Okay, so there is one big peak at 60 hertz. 60 hertz is the power line in US, for instance. So in Virgo you would see at 50 hertz, because in Europe it's 50 hertz. Then here are suspensions. I mean, Irene told you that mirrors are freely falling. She lied, no? I mean, if they were freely falling, they would smash down and you have to rebuild them every second. No. They are hanging, of course. They are freely falling in the XY direction, but in Z direction, they're not freely falling, no? And to be hanging, I mean, there must be a thread of some kind, and this thread will have some, like you solve in physics 101, no? 2 pi square root of L over G. It has its own frequency. And if a perturbation arrives exactly that frequency, there is no way you can screen. I mean, you can screen it, the pendulum, to most of the frequency, but if it really hits the resonant frequency of the pendulum, it's very hard to screen, and that's why you get. So and then you have pendulum in cascade. So the lower pendulum in the screens the frequency of the upper one, and vice versa. But some lines remains. I mean, there's no way. So these are basically suspension lines, the very narrow ones. This one, I don't know. This one is 60 hertz. This one I don't know. All these other ones are suspension lines. Yes, and I mean, you have to deal. But those are not really bothering because they're very narrow. So if you look at the Fourier transform of this in time domain, the time profile of the output of the detector will be dominated by this line, the time. But when you go to Fourier space, it's very easy to cut them. You just throw away everything which is in this narrow frequency band, and then you go back to time. And so you will see a much lower noise level. So these are not really a problem, provided that they are narrow.
Yes,
If they are narrow, they're not a problem.
You need to remove them.
Yes.
All of them, yeah.
Yes, and
Even the one
that's pretty straightforward to do for narrow lines.
Thank you.
Okay. Go now.
Hi. So the fun fact you mentioned about the amplitude of the waves not depending on the redshift.
Yes.
So you mean eventually if we build sensitive detectors, we can see the Big Bang?
No, but as I said, because if you go backwards and backwards, the signal is shifted towards smaller frequencies.
Yeah.
And eventually, no matter what is the bandwidth of the detector, if you keep going to high redshift, then you keep going to smaller frequency, eventually you fall out of your detector bandwidth. So what really matters is not only this, but really matters the detector bandwidth.
Okay.
So, for instance, I can give you a spoiler. There is it's not really a detection, but has anybody told you about pulsar timing array? Maybe somebody works here, in pulsar timing array. Yeah, you. Oh, okay. So, okay. I don't want to put you in the spot, but there is a kind of the detection that has been made by pulsar timing array. So they are looking at the signal of pulsar from our galaxy, and there is a correlated disturbance. What can it be? It must be a gravitational wave. So what is the frequency range? It's very different from LIGO because they are observing over the time scale of years, and they see disturbances of the observation time. So 1 year is pi 10 to the 7 seconds. This is another fun fact for you to remember. 1 year is made of pi times 10 to the 7 seconds. This is correct to 2 digits, to 3 digits. Okay, and so the frequency related to this is less than 10 to the minus 7 hertz. So at 10 to the minus 7 hertz, there is a possibility of a signal, which to be confirmed needs more, how many more years of data to get to 5 sigma? 2 more years? In 2 more years, you should be prepared to have a detection of gravitational wave at 10 to the minus 7 hertz. That would be mind-blowing. And so the following day, I'm sure you will have theorists, clogging the archive with a zillion of explanation of this. But anyway, just I'm sure he will get the Nobel Prize. I mean, after the detection is confirmed. I mean, it's not confirmed yet because you have to accumulate more data to exceed the 5 sigma. But if the data keep flowing the way they seem to flow, then in few years' time there will be detection of gravitational wave stochastic probably, or maybe some superposition of astrophysical signal and 10 to the minus 8 Hertz. It will be really complementary to LIGO and LISA.